Okay, so in this video, we're going to talk about something called an impulse train. Okay, so we're going to talk about impulse trains. And let me just draw one. So what does it sound like? An impulse train, a train of impulses. People use the word train, but it's just a sequence of impulses, kind of a train one after another of impulses, delta function. So I'll just draw that. Here's what it looks like. Pretty simple, actually. Okay, just a whole bunch of delta functions. Okay, and they go on forever and ever, periodically. And I'm usually going to use the letter S for an impulse train, and we'll see why when we get to sampling. Okay, but right now I'm just going to use S of t. Okay. And so these are going to each have some sort of period. In this case, I'll just call it t. Okay, and so these delta these delta functions are just going to repeat forever and ever, every t, big T time units. And I'll just make them all of height 1, but that is not necessary for an impulse train, as I'll write down in 1 second, but just as an example, I'll just use 1. So in this case, what is S of t? It's just a big sum of delta functions that are all scale or that are all shifted by integer multiples of this t. So that's fine. We just take our delta function delta of t and we shift it by integer multiples of t. Okay, so this equation is describing exactly the picture above. So now let me just give you the definition. An impulse train, okay, that was an example, just so you could get it in your head. Okay, it's just a train of impulses. Specifically, it's a sequence of equally spaced. Okay, so you can see that all of these impulses are spaced out by big T. So equally spaced delta functions. Okay, and we're also going to require that they all have equal area. So you can see that all of the areas or heights as we draw them of these delta functions I made in that picture equal to 1. But of course, we could just multiply everything by A and have all their heights be A. Okay, but I'm just going to keep it as 1 just for an example. But we do require that an impulse train, they all have equal area. Okay, and that's it. That's all an impulse train is. And something we're going to be interested in is the Fourier transform. So let's find the Fourier transform of the impulse train above, which is S of t. Okay, so this is something that we're going to be interested in some future videos. So let's talk about it right now. Okay, so how should we go about finding the Fourier transform of this impulse train? Well, we can see that it's periodic, right? S of t is a periodic function, okay? And so what we can do is we can find its Fourier series and then take the Fourier transform of that Fourier series, as we saw in a previous video. And then we'll get the Fourier transform of this impulse train. So I'm going to write that. So S of t is periodic with period t. So we can write its Fourier series. Okay, so what would that be? That would be S of t is going to be a big sum of these complex exponential functions. Remember, omega naught, the fundamental frequency, is just 2 pi over the period. Okay, and we're going to multiply them by Fourier series coefficients, which I'll write as capital S sub n. Okay, so those are the Fourier series coefficients, so let's find them. Let's find the Fourier series coefficients S sub n. Okay, so we know how to do that. This would be a good practice problem if you want to just pause the video and try this on your own first. Okay, but these Fourier series coefficients S sub n, we know that they're just 1 over the period times the integral of the period of the function S of t times e to the negative j n omega naught t dt. Okay, so now what can we do? Well, we have to pick where we're going to integrate. We have to integrate over a period, so let's go up. What would be a nice period to integrate over? Well, I think just a really simple period from maybe negative t over 2 to t over 2 would be really nice, because then we just have that one perfect delta function centered at 0, and that's all we have to worry about. Okay, so I'm just going to take that period, but of course, many others work as well. Any other. So we're going to integrate this over a period, and I'll just use the period that I picked. So negative t over 2 to t over 2 of s of t, e to the negative jn omega naught t dt. Okay, so now we are integrating this function. And as we've seen before, the next step that we usually perform is to say, all right, well, on this period, what does my function s of t equal? Because then I can just substitute in for s of t for hopefully a simpler function where they happen to be equal on this place that I'm integrating over. Okay, so if I'm integrating from negative t over 2 to t over 2, what does my function s of t equal in this range? You can see it just equals delta of t. S of t just equals delta of t between negative t over 2 and t over 2, right? So it's really nice. So if that's the case, and I'm only integrating over that range, I might as well substitute in that simpler function for s of t. Delta of t, e to the negative j n omega naught t, and I'll just write it over to the side. So this is when t is in that range. Okay, s of t actually just equals delta t in that range. That's how we were able to do that. Okay, and now what do we have? Well, now we just have an integral of a delta function times another function, and we know what happens when we have that situation. That whole integral, all it does is it picks out the value of the thing multiplying the delta function, evaluated at the place where the delta function is located. So this delta function, of course, is located right at t equals 0. So this entire integral is just going to pick out the value of this function evaluated when t equals 0. Okay, so I'll write that. So times e to the negative j n omega naught times 0. But of course, we know e to the 0 is just 1. So we end up with 1 over t. There we go. Those are our Fourier series coefficients s sub n. And so we can actually see in this case, the Fourier series coefficients s sub n, which equal 1 over t, they actually don't depend on n at all. They're constant for all n. Okay, so in this case, for an impulse train, the Fourier series coefficients are all the same number, 1 over t. They're constant for all n. Okay, so what does that mean that the Fourier series of s looks like? Well, all we have to do is plug in for s sub n, and we're just going to plug in 1 over t everywhere. So I just get 1 over t times the sum of these exponentials, or sorry, little t. Okay, this is the Fourier series for s of t. We just plugged in for the coefficients. Okay, so what does that mean for the Fourier transform? Okay, we saw this in a previous video. The Fourier transform of a Fourier series, what happens? Well, we just get a big sum of delta functions in frequency that are shifted by all of these integer multiples of the fundamental frequency. And what number is multiplying those delta functions? Well, as we saw in a previous video, this was the Fourier transform of a Fourier series video. Okay, we saw that the things multiplying the delta functions are not quite just these coefficients, they're actually those coefficients times 2 pi. Okay, so you can review that video Fourier transform of a Fourier series if you don't remember that. And now I'll just make one little substitution because we know 2 pi over t is actually the fundamental frequency. Okay, so we really just get the fundamental frequency times this big sum of shifted deltas. And so what can we say about this? Well, maybe once I draw it, you'll kind of see it more clearly, although you can definitely see it now already. So what do I get? I just get a bunch of these delta functions in frequency forever and ever. And what are they spaced out by? They're spaced out by integer multiples of omega naught. They go on forever, and they all have the same height. They all have the same height, omega naught, or area, omega naught. This is my S of omega. So what can we say? Well, wait a second. S of omega, the Fourier transform of our impulse train, is itself an impulse train. So S of omega is an impulse train in frequency. Okay, so that's kind of a nice thing to just keep in the back of your head, that when you have an impulse train in time and you take the Fourier transform, you get another impulse train in frequency. How is that impulse train different than the original? Let's just compare. The original impulse train had delta functions, at least in this case, that all had height or area 1, and they were at shifted multiples. They're at integer multiples of the period, t. And then when we take the Fourier transform, now we have a bunch of delta functions that their heights have been scaled by the fundamental frequency. And now these delta functions themselves are located at integer multiples of the fundamental frequency, but it's still an impulse train. Okay, so let me just summarize that with some pictures. So I'm going to draw two different impulse trains on the left and draw both of their Fourier transforms. Okay, so let's say I have this impulse train in time. Make it symmetric. Okay, so this goes on forever and ever. This is 0. Let's say this is t and negative t and so on. And let's say they all have height 1. Okay. That's one impulse train in time. And I've drawn this to show you an impulse train with a small period in time. And I want to compare the Fourier transform. I want to see what happens compared to an impulse train that has a large period. Okay, so this will be negative t, this will be t. They both are periodic, they go on forever and ever. Okay, so this is a large period in time. Okay, and let's see how the difference in their periods affects their Fourier transforms. Okay, so when I have a small period in time, what happens when I take the Fourier transform? Well, what we have to figure out is what these omega naught values are. And remember, 2 pi over t equals omega naught. Okay, so the smaller I make the period, you can see the period and the frequency are inversely related. The smaller I make the period, the larger the frequency gets. And the larger I make the period, the smaller the frequency gets. Okay, so if I have an impulse train that has a small period in time, they're all scrunched together. Okay, these delta functions are happening very quickly. In frequency, that omega naught is going to be large. And so what I get is delta functions that are spaced out. There's a large period in frequency because the period in frequency now is omega naught, which as the period in time t gets smaller, this gets larger. Okay, these all have height omega naught, so I've drawn them a little bigger as well. Okay, but this is a large period in frequency. And what happens when I have a large period in time? Well, the larger this big T gets, the smaller omega naught gets. Okay, so what I'm going to end up with in frequency is something that looks like this. I've also drawn the heights to be smaller because remember the heights are all omega naught. Okay, so this is a small period in frequency. Okay, so this is kind of the main picture you should think of when you look at an impulse train. These all have height 1. Okay, when I have an impulse train in time, I get an impulse train in frequency for the Fourier transform. And also, this is going to be important when we get to sampling. The smaller I make the period in time, the more I have these impulse trains, these delta functions in an impulse train squished together, the farther spread out they are when I take the Fourier transform, versus the larger the period is in time, the more spread out they are in time. In the second example, the more pushed together they are in frequency. Okay, so this is kind of this inverse relationship summarized by this equation right here between the period and the frequency and how it plays a role for impulse trains. Okay, so yeah, so that's what an impulse train is and a little bit about its Fourier transform. That's all I had for this video, and I'll see you in the next one.